This lesson has been developed in the framework of SCILED project.
Module 1, Footwear Performance and Comfort. Unit 5, Testing Standards and Equipment for Evaluating Comfort and Performance.
Lecture 5.1. Testing Standards and Equipment for Evaluating Performance Aspects. This lesson is structured as follows: Essential Assessment for Materials, Components and Footwear, Slip Resistance, Water Resistance, Microbiological and Odor Assessment. Essential Materials, Components and Footwear Assessment. This is the outline for the Essential Materials, Components and Footwear Assessment, where there are presented testing methods and recommended values for upper and lining materials and products, bottom materials and products, upper bottom parts adhesion materials.
Abrasion. Martindale. The Martindale test is an abrasion test related to the resistance that a material can handle when it is subject to friction. In the Martindale test, 4 circular test specimens are rubbed against pieces of a standard abradant fabric or a standard abradant paper under constant pressure, with 2 of the pieces of abradant dry and 2 wet. The relative movement between the abradant and specimen is a complex cyclic pattern which produces rubbing in all directions. The specifications and requirements for Martindale are found in ISO TR 20882, Footwear, Performance Requirements for Components for Footwear, Lining and in Socks. The evaluation is made by visual analysis, where in dry conditions after 25,600 cycles, the values are not worse than moderate degree, and for wet conditions after 12,800 cycles, the values are not worse than moderate degree.
The resistance to flexion tests simulate the usage of materials to evaluate its suitability to be applied on footwear. The standard ISO 17694 specifies a test method for determining the flex resistance of uppers and linings irrespective of the material in order to assess the suitability for end use. The evaluation is made by visual analysis, where for leather uppers under dry conditions after 80,000 cycles and wet conditions after 20,000 cycles, there is no visible damage, and for coated leather, there is no visible damage after 20,000 cycles at -5 degrees Celsius. For other materials under dry conditions after 80,000 cycles and after 20,000 cycles at -5 degrees Celsius without visible damage. For lining under dry conditions after 15,000 cycles, there is no visible damage.
Tear strength is the force required to tear a material. The ISO 17696 standard specifies a test method to assess the tear strength of uppers, linings and in socks or complete upper assembly, irrespective of material, in order to assess the suitability for the end use. The recommended values for uppers is to be greater or equal to 40 Newton and for linings is greater or equal to 15 Newton.
The color fastness is the persistence of color. Several tests can be made to simulate the use of a material and evaluate the color fastness of diverse materials in several conditions. It can be evaluated by rubbing the sample materials with a standard material in dry conditions, with artificial human perspiration or with water. The standard usually includes one or more test methods in which the rubbing apparatus and conditions are described. The evaluation is made by visual analysis, where for uppers, the inside of unlined footwear, if method A is used, is greater or equal to degree 2/3, grayscale, after 50 cycles with artificial perspiration solution. For the outside surface, the color change and staining, if method A is used, must be greater or equal to degree 3, grayscale, after 150 cycles in dry conditions and 50 cycles in wet conditions, normally water, or if method B is used, the color change and staining must be superior or equal to degree 3 to 4, using grayscale, after 512 cycles in dry and 128 cycles in wet conditions. For linings, the inside staining, using method A, is greater or equal to degree 3 after 50 cycles with a perspiration solution.
Abrasion is the property related to the resistance that a material can handle when it is subject to friction. The abrasion tests for bottom materials involve the evaluation of their surface resistance with an abradant material or a mechanical machine. Usually, the standard ISO 20871 EN 12770 is used to perform this test on outsoles. The recommended values are as follows. If the density is less than or equal to 0,9 grams per cubic centimeter, the abrasion value should be inferior or equal to 250 cubic millimeters. If the density is greater to 0.9 grams per cubic centimeter, the abrasion value should be inferior or equal to 170 cubic millimeters.
Flexion. Footwear bottom materials and components are frequently required to resist repeated flexing without breaking. The use of materials that are not flexible requires that design introduces features that allow use of the footwear. Flexion resistance is the number of flexes that cause cut growth and/or initiation of cracks or otherwise fail at flex increases. The recommended values is referring to the cut growth, which has to be less than or equal to 5,0 mm and without spontaneous crack. Tear strength is the force required to tear a material. The recommended values are as follows. If the density is less than or equal to 0.9 grams per cubic centimeter, the tear strength value should be superior or equal to 8,0 Newton per millimeter. Or in the case of the density being greater than 0.9 grams per cubic centimeter, the tear strength value should be superior or equal to 6,0 Newton per millimeter.
Upper-bottom parts adhesion. Adhesion is the state in which two surfaces are held together by interfacial forces. Standard EN 17708 gives a test method to determine the resistance to separation of the upper from the outsole, to separation of adjacent layers of the outsole, or to tear failure of the upper or the sole. It also defines conditions of aging that can be used for production control. It applies to all types of footwear, cementing, vulcanization, injection molding, and others, where the evaluation of sole adhesion on the upper is needed and where the upper is continuously assembled, closed shoe. The specifications and requirements are for the eco-label for footwear. The recommended values for leisure footwear for adhesion is equal or superior to 3 Newton per millimeter.
Slip resistance. Slip resistance is linked to the coefficient of friction between soles and the floor in which the footwear is used. The standard ISO 13287 describes a method to evaluate the slip resistance of personal protective equipment footwear. In this test method, the footwear is placed on a surface, subjected to a given normal force, and moved horizontally relative to the surface, or the surface is moved horizontally relative to the footwear. The friction for and the normal force are measured and the dynamic coefficient of friction is calculated. The footwear shall be tested in one or more of the following modes. Forward heel slip at angled contact. Backward slip on the forepart. Forward flat slip. The heel test mode is considered to be the most important in relation to reducing the risk of pedestrian slipping. The footwear can be tested on different floors and conditions, for example, ceramic tile floor with NILS, steel floor with glycerin. This test can also be performed on an ice floor or other that we would like to test for a specific application.
The recommended values for occupational footwear on ceramic tile floor with SDS are as follows. Condition A, forward heel slip, the coefficient of friction shall be greater than or equal to 0,28. Condition B, forward flat slip, the coefficient of friction shall be greater than or equal to 0,32. In the case of occupational footwear on steel floor with glycerin, condition C, forward heel slip, the coefficient of friction shall be greater than or equal to 0,13. Condition D, forward flat slip, coefficient of friction shall be greater than or equal to 0,18. Now going into the ramp test. The ramp test can test floors and footwear and the result is provided in coefficient of friction. This test classifies footwear as high, moderate or low slip potential on a given surface with a given contaminant. Research indicates that this test distinguishes footwear with poor, average and good slip resistance. Specifications and requirements are found in BS 4592, flooring, stair treads and handrails for industrial use. Common design requirements and recommendations for installation. The recommended values are as follows. Unsuitable for foreseeable wet conditions if coefficient of friction is less than 0,4. Suitable use in wet conditions if coefficient of friction greater than or equal to 0,4. Enhanced slip resistance if coefficient of friction greater than or equal to 0,6. Water resistance.
The level of water resistance of footwear materials can be tested by using the Bally Penetrometer and Penetrometer tester. There are also available test methods to evaluate the water resistance of whole footwear. These test methods will be addressed in the following slides. Bally Permeameter Test. Bally Penetrometer is applicable to all flexible leathers but is particularly suitable for leathers intended for footwear uppers. In these tests a piece is formed into the shape of a trough and flexed whilst partially immersed in water. The time taken for water to penetrate through the test piece is measured. The methods also allow the percentage mass of water absorbed and the mass of water transmitted through the test piece to be determined. The recommended values for casual footwear is as follows. Water resistant, penetration time greater than or equal to 60 minutes, where the absorption after 60 minutes is 20% or less. Highly water resistant, penetration time greater than or equal to 180 minutes, the absorption after 180 minutes is 25% or less. The recommended values for occupational footwear are, water penetration after 60 minutes shall be 0,2 grams or less and the water absorption 30% or less.
Miser Water Penetration Test. The Miser Water Penetration Test is more stringent than the Bally Penetrometer Test. This test covers the determination of the dynamic water resistance of shoe upper leather and is applicable to all types of shoe upper leather. The flex imparted to the leather is similar to the flex made by the vamp of the shoe in actual wear. To have an idea, 50,000 Miser flexes, taken over a period of about 8 hours, is the equivalent of more than 70 kilometers of treading in water. The recommended values are divided in 3 categories according to the resistance. Medium resistance for 1,000 to 5,000 flexing cycles. Good resistance for 5,001 to 10,001 flexing cycles. Excellent resistance for higher than 10,001 flexing cycles.
Water resistance of heavy leather. Test method applicable to soles made of leather. The test piece is continuously wet on one surface and is flexed and compressed in the same manner as the sole of a shoe during walking. This enables various aspects of heavy leather water resistance to be measured with respect to time. The recommended values are as follows. A leather is considered water resistant if for a penetration time higher or equal to 30 minutes the water absorption after 30 minutes is 25% or less. And is it considered highly water resistant if for a penetration time equal or higher than 60 minutes the water absorption after 60 minutes is 15% or less.
Dynamic test. The dynamic test method is used to evaluate the resistance to water penetration of a whole footwear during flexing and can be applied to all types of footwear. Basically, the shoe is secured in a flexing machine with water at a defined level above the feather line. The footwear is flexed at a constant rate and inspected for water penetration. This test is intended to simulate the flexing force performed during the walking movement. The recommended values are as follows. The total wet area inside footwear less than 3 squared centimeter of water penetration after 100 trough lengths.
Machine scrubbing test. A complementary test is based on a machine with brushes and water jets. In this method the whole footwear submerged in a defined depth of water is subjected to the mechanical action of rotating wet brushes. The extent of water penetration is determined by examination. The shoe is fixed in a rectangular metal plate with a fixed jaw at one extremity and a sliding jaw at the other to adjust to the height of shoe. Then 2 brushes situated on either side of the test piece are separated by adjusting a distance describing a backwards and forwards motion over the whole length of the test piece, whatever its size. The horizontal motion of each brush is completed by a rotational movement, the direction of which changes at the end of each horizontal cycle. The direction of rotation of each brush is the same as the corresponding backwards or forwards motion. The horizontal distance between the 2 brushes system should be adjusted so that the whole surface of the footwear upper touches the bristles. This test method is useful to evaluate if the shoe just has a superficial water repellence treatment. The passage of the brushes will remove the superficial treatment and evaluate effectively the water resistance of the shoe. Recommended values: total wet inside footwear less than 3 squared centimeter of water penetration after 80 minutes.
Trough test. Regarding the water resistance of footwear, the trough test allows one to determine the water resistance of footwear, irrespective of the material. In this test a pair of footwear is worn whilst a measured number of paces are walked over a surface flooded with water to a measured depth. The extent of water entry is determined by inspection. After 100 trough lengths, the footwear is carefully removed, and the inside is examined visually and by touch for signs of water penetration. If any penetration has occurred, The position and extension should be recorded on diagrams for each boot or shoe. The recommended value is, water penetration shall not occur before 15 minutes of test. Microbiological and odor assessment.
Microbiological aspects. Microbiological tests are more and more often used for evaluating footwear and footwear components due to the development and introduction in the market of antimicrobial materials to be used on footwear. The presence of microorganisms inside the footwear can have different implications, which includes degradation of the materials, development of some foot diseases and development of malodors, due to the degradation of sweat and material constituents. Footwear is a closed system with the optimal environment for the development of microorganisms, due to high concentration of CO2, temperature, moisture accumulation, and lack of light. These are optimum conditions for some bacterial and fungal growth. To prevent unpleasant odors, foot diseases, and footwear material degradation, it is important to understand the role of microbiological tests in footwear.
There are two bacterial tests, the antibacterial activity and zone of inhibition. Antibacterial activity is the efficacy of a material or finish used to prevent or mitigate the growth of bacteria, to reduce the number of bacteria or to kill bacteria. The test described in Standard ISO 16187 specifies a quantitative method to evaluate the antibacterial activity of footwear and footwear components. In this test, the material to be tested is in contact with the bacterial organisms, and after a contact time of 24 hours, the bacterial population is analyzed in order to calculate the antibacterial activity ratio. It allows the determination of the antibacterial activity ratio of a treated sample individually or the comparison of treated samples versus untreated samples. Two strains are used, Staphylococcus aureus, gram+, and Klebsiella pneumoniae, gram. Other species or other strains can be used, but at least 1 gram+, and 1 gram. If the whole footwear is claimed to be antibacterial, major components, including upper, lining, insock, outsole shall be tested separately. 3 testing methods are possible. Method A, static challenge test for absorbent materials, for example, textile and leather. Method B, film contact test method for non-absorbent materials, for example, microporous/expanded materials and compacted materials. Method C, dynamic challenge test for absorbent and non-absorbent materials, for example, components of different materials, shaped materials and materials with fixed antibacterial agent. Independently of the method used, 2 strains of bacteria must be tested and have to include a bacteria gram-positive and a bacteria gram-negative, in order to claim antibacterial activity. The final result of this test is an antibacterial activity ratio for each bacteria. The specifications and requirements are that the antibacterial activity rate shall be greater than 90%. However, this value shall be higher than 99.9%.
Standards ISO 20645 and OC 147 describe methods to determine the effect of antibacterial treatments applied to woven, knitted, other flat textiles and other materials by evaluating the zone of inhibition. There is another type of test that uses the formation of a zone of inhibition to bacterial growth. The zone of inhibition occurs as a result of the diffusion of an antibacterial agent on the materials that are being tested. The bacterial growth under the material surface can also be analyzed. The standard ISO 20645 specifies a method for the determination of the effect of antibacterial treatments applied to woven, knitted and other flat textiles. This method is applicable to testing hygienic finishes of hydrophilic, air-permeable materials or antibacterial products incorporated in the fiber or material. A minimum diffusion of the antibacterial treatment into the test agar is necessary with this procedure. The standard OC 147 describes how to detect bacteriostatic activity on textile materials. The method is useful to obtain a rough estimate of activity in that the growth of the organism decreases from one end of each streak to the other and from one streak to the next, resulting in increasing degrees of sensitivity. Specimens of the test materials are placed in intimate contact with the agar surface which has been previously streaked with the organism. After incubation, a clear area of interrupted growth underneath and along the side of the test material indicates antibacterial activity.
The antibacterial effect is assessed by analyzing the growth of bacteria under the test sample and the extension of the zone of inhibition. If the inhibition zone mean value is between 0 and 1 mm and less than 1 mm, no growth under the specimen, it is classified as good effect. If the inhibition zone mean value is 0 mm and there is a slight growth under the specimen, it is classified as limit of efficacy. If the inhibition zone mean value is 0 mm and there is a moderate or heavy growth under the specimen, it is classified as insufficient effect. The recommended values for ISO 20645 and OC 147 are no growth of bacteria in the nutrient medium under the test specimen.
Antifungal activity is the efficacy of a material or finish used to prevent or mitigate the growth of microfungi, to reduce the number of microfungi or to kill microfungi. The standard ISO/DIS 20150 gives a method for determining fungal resistance of footwear and footwear components. It describes how to determine antifungal activity of footwear and footwear components. The test described in standard ISO/DIS 20150 specifies a quantitative challenge test method for evaluating the antifungal activity of footwear and footwear components. In this test, the materials and controls are inoculated with a suspension of fungi of a selected test strain, specified or claimed. Antifungal performance is quantitatively determined by counting the number of viable colonies and calculating the antifungal activity ratio. If activity against mold is claimed, testing of one mold strain shall be performed. If activity against dermatophyte is claimed, testing of trichophyte and metagrophytes shall be performed. Please note that if the whole footwear is claimed to be antifungal, major components, including upper, lining, and sock, outsole shall be tested separately. The recommended values are as follows: antifungal activity rate greater than 90% for 2 strains, ideally this value shall be higher than 99.9%.
Qualitative test. Evaluation of the antifungal activity of footwear and footwear components due to the action of microfungi. The standard ISO AWI 19574, under development, specifies a test method for a qualitative evaluation of the antifungal activity of footwear and footwear components due to the action of microfungi. Just like bacterial tests, there are other alternatives to quantitative test methods, like qualitative test ISO AWI 19574. This test, still in development, is qualitative, and allows one to evaluate the ability of materials to inhibit fungal growth. ISO AWI 19574 method evaluates the growth of fungi organisms after at least 28 days of incubation of specimens in optimal fungal growth conditions. The assessment of fungal growth is made by visual examination on the exposed specimen's surface. The antifungal performance is qualitatively determined by a visual assessment of fungal growth after a specified or agreed period of incubation, and the recommended result is no fungal growth under the microscope, magnification 50 times.
Mold growth resistance. The standard ASTM D4676 provides a technique for evaluating mold growth resistance characteristics of leather in wet blue and wet white stages and should assist in the prediction of storage time before molding occurs. This test method covers the determination of mold growth resistance of wet blue and wet white subject to storage and shipping requirements and intended for use in leather manufacturing. This test method may not be suitable for evaluating fungicides that are inactivated by proteins. The mold growth resistance is evaluated by simultaneously running a control of known resistance with the sample that is in evaluation. Success or failure is determined by the amount of mold growth relative to the control. The fungal growth test method is based on fungal growth in temperature and humidity conditions. Another approach is to evaluate the fungal growth in conditions of temperature and humidity, during a defined period of time, 14 to 28 days, with no inoculation with suspension of fungi.
Odor is evaluated by a trained panel for odor evaluation. It's well known that in shoe malodor associated with footwear use may be due to the degradation of organic sweat and material constituents. Nowadays, companies and clients are more sensitive to this problem and often look for a solution in selecting footwear and their components. Odor can be analyzed by trained persons constituting a sensory panel that performs an odor evaluation according to defined scales of intensity, pleasantness and durability of odors or fragrances on materials and components for footwear and, when possible, identification of the compound responsible for the odor. Electronic nose devices can also be used to identify and analyze specific components of an odor. These devices consist of a mechanism for chemical detection, such as an array of electronic sensors, and a mechanism for pattern recognition, such as a neural network. This solution can be used to evaluate the footwear materials, after use, to quantify the molecules that are associated with feet malodor, for example, isovaleric acid.
Electronic nose devices can also be used to identify and analyze specific components of an odor. These devices consist of a mechanism for chemical detection, such as an array of electronic sensors, and a mechanism for pattern recognition, such as a neural network. This solution can be used to evaluate the footwear materials, after use, to quantify the molecules that are associated with feet malodor, for example, isovaleric acid.